Hello, welcome to our lesson for 5.7. Today we're going to be looking at how to graph or how to hand draw the graph of the first derivative of the function. Now, where can you find these notes? I've just made a version of notes that would be easy for you to follow. If you have a printer at home, you're welcome to print this. If not, when you get to school tomorrow, I'd be happy to share that with you. You can also make a copy of this particular PDF page onto your own OneNote. All right, let's get started here. So far, we've already looked at a few examples where we start off with f of x, and then we can roughly sketch what the first derivative graph looks like. Now, we're not talking about exact points necessarily, but at least we know the ups and downs of what our graph is going to look like just based on the curve, or based on the slope direction. Now, here's what we need if we want to go from original function into the first derivative. We need to spot the stationary points because these become the roots. So a quick reminder here what stationary points are. I know we haven't exactly defined this term, but we've been using the word stationary points for whenever the first derivative is going to equal 0. So this is our maximum, our minimum, and as we most recently saw in the last lesson, sometimes it's not a maximum or a minimum because the direction continues to be exactly the same, and these were the points of inflection. These become roots, and what we mean by roots, of course, is that the output is equal to 0, which means you're able to solve for what is the x value at these particular points when the output is equal to 0. Now, sections where your original graph, so increasing sections in f of x, have positive first derivative, so above the axis, meaning basically your slope is positive. And vice versa, decreasing f of x sections have negative slope. Let's draw this out and see what that looks like here. So let's say I have an original graph that looks like this. And I'm just going to label this F for being the original graph here. We can see that we've got this maximum and minimum here. And part of our practice is just trying to figure out, okay, what would it look like if I have a rough sketch also of my first derivative. So I'm just going to use my ruler to kind of help me pinpoint that. My maximum point then is going to be here, and I know that maximum is going to reflect as a root since the slope there is 0. At my minimum, again, the slope is going to be 0 in my first derivative graph. So that's my first derivative. In this first section, I have a positive slope. So that means somehow my graph needs to be above the x-axis. Middle section here, the slope is negative up until it becomes 0. So I know that graph is going to be somewhere down over here. And of course, it becomes positive again towards the end. So I'm going to be somewhere up here. Okay, so how do we draw this first derivative graph? There's no science to it. It's just saying, okay, somehow this needs to be above, somehow this needs to be below, and it needs to go back up again. Okay, and that's all we need here. And again, that's just reflecting our first statement here that they become roots. The stationary points right here become our roots. Now I've drawn a third line on the bottom of this notes template here. So you can see there's something else we're trying to pick out here. There's one more point in the original graph that we started discussing last lesson, and that's somewhere over here. Maybe I'll use a blue marker here. Right here, and that would be our point of inflection. Now, it's not something we can immediately spot from the original graph, at least not accurately, but we can see that in the first derivative graph here, because that point is a minimum. So this is a stationary point in my first derivative graph. And I can take the same point, and I'm just going to bring this down here to my second derivative. Now, second derivative is talking about the slope of the first derivative graph. And I know that at this minimum, the slope has to be 0. So I'm going to have a root right here. Now, the question becomes, what happens to the rest of my second derivative graph? And there's 2 points we can look at here. One is in my first derivative graph, all of this here, that's a negative slope. That's going downwards, okay? So I know that this part of my graph is going to be on the negative side, okay? This is going to be on the negative side. And then on my right-hand side of my first derivative graph, this is all positive. So I know that my second derivative graph is going to exist up here. Okay, and the slope is consistent, as in it's a smooth parabola here. So we know actually that our slope for the second derivative graph is going to be a straight line. It doesn't have to be perfect, okay? I'm just going to draw a straight line to illustrate that. And that's all we need to do here. Meaning things that we can actually see. If we were to take the original graph, so from, and I'm going to make some changes here to my notes and you'll get a better copy there. From the original f of x to the first derivative graph, any points of inflection in the original graph, so right here, becomes a minimum or a maximum in the first derivative graph, right here. And if we were to go from the original graph, f of x, to the second derivative, any points of inflection then looks like a root in the second derivative graph. Okay, so just ignore this typo right here. Okay, let's try drawing these three graphs together here. My first one is the original graph, and our second one is going to be the first derivative, and of course the second derivative. So we're going to start with our stationary points, and those have already been labeled for you with a red X right there. Again, stationary points, these are your local maximum, minimum, and any kind of stationary inflection points. Now, as I use the word stationary inflection point, you might be wondering, hold on, can an inflection point be non-stationary? Absolutely. Remember, an inflection point is where the curve or the concavity of the curve changes. So that's our inflection point right there. But when we're talking about stationary inflection points, the concavity of the curve is still changing, right? Like this is concave down technically, this is concave up. Again, technically, because it doesn't look like our drastic curves there, but that red dot in the middle there, that's an inflection point because the concavity changes. But we also have a perfectly horizontal slope at that particular point, and that's where we get these stationary inflection point. Sorry, I've labeled it as if it's non-stationary, but in fact it is stationary. So going back to what we learned last lesson, these stationary inflection points, you can get this from just doing first derivative. These non-stationary inflection points, you have to take the second derivative in order to get the non-stationary inflection point. So the most common types of points of inflection. All right, going back to our example now, we have our three stationary points, and with these stationary points, the first thing we're going to do when illustrating first derivative of f of x is we're going to mark down all three of these stationary points as when the first derivative is equal to 0. In other words, our roots. Okay, so I've marked those down. And next, you're just kind of eyeballing, okay? So my slope is increasing here, and increasing here, which means in all three of these sections, your first derivative graph is going to be above the x-axis. Again, above the x-axis just tells us we have a positive slope. So I'm just going to highlight, okay, that those are the areas it's going to be. The only part that has a negative slope is here, so I know my graph is going to be somewhere down over here. Besides that, I can see that there is a greater increase in this area, which means I'm going to have a slightly higher value. But honestly, you're just eyeballing here because we don't have an exact coordinates, so I'm going to roughly mark that down. Again, this area I can see is quite steep, so very positive. So maybe it goes up here again. And again, this area very steep, so maybe somewhere over here. Okay, and the next thing you have to do then is just join the lines together. I'm going to join my lines as best as I can, going down to the negatives, connecting all of my roots here, something like that. So I go down to my root again, but then we go back up at this point, okay, positive slope. And the slope seems to be increasing, but who knows? So roughly, that's going to be what my first derivative graph looks like. Now let's move on to our second derivative graph, okay? So where my first derivative graph was 0, so I had a root, it doesn't mean it's 0 over here. In fact, it's not. All that's happening to that slope is it's a negative slope, Okay, so I'm actually going to go back here and maybe I'll use a different color here. I see here, this is all negative. Negative. And then on my positive side, this is positive and this is positive. So I'm going to repeat the processes I did between the original graph and my first derivative. But this time I'm going to do that for my first derivative and second derivative, which means I'm going to be looking for my stationary points in the first derivative graph. So there's my minimum, my maximum, and my minimum. Oops, my minimum again. All three of these points must be 0 in my second derivative graph. So I'm going to draw those in. And again, I'm seeing here, this part is negative, this part is negative. These parts, I'm going to have a positive graph. So very roughly drawing that out, I'm going to have a graph that looks like this. Okay, something like that, going down to the negatives. All right, and you'll see that the maximums and the minimums from my original graph doesn't translate down to anything in particular in my second derivative graph, but the stationary inflection point transfers down to be 0 in both my, the output turns out to be 0 in both my first derivative and my second derivative graph. And there is one more point that is also 0 in my second derivative graph that we hadn't seen previously, and that's where that maximum we saw in the first derivative graph is. And you can see that this particular point, what is that in my original graph? Well, that's a point of inflection that was non-stationary. We don't call it non-stationary points of inflection, we just call it points of inflection. But for our learning purposes, it wouldn't hurt to label that non-stationary versus the one that we spotted using the first derivative of f of x, which was stationary. This is a really good graph to kind of refer back to. And from this graph, I'm going to give you a quick trick here for going backwards to drawing the original graph. Because again, oftentimes you'll be asked exactly that. In your first derivative graph, if you spot a root, okay, so depending on what your roots look like from your first derivative graph, if your root looks like this, so this first purple line, then you have in your original graph a maximum. And that makes sense because we're saying the slope went from being positive to negative, so then we have a maximum. Similarly, or rather vice versa, if you have a graph that looks like this, okay, so we're saying your graph started off on the negative side, ended up on the positive side, then you must have a local minimum. So we see that example in our graph right here. And then you have the situation where your graph actually, for the first derivative graph, it stays positive. So it looks like this. It means you're going from the positive side to the positive side again. Or it stays negative, okay? It starts off negative and then you hit a root and then it continues on negative. In these cases, you must have a stationary inflection point or point of inflection.